Chapter 14.4 Using a regression to make a prediction. As mentioned earlier, we can use our regression equation to predict the grades we would expect students to get based on the number of hours they spend studying. Earlier in the chapter, we figured out that a student who studies 3 hours could expect the following grade. Y cap equal to 70.11783 plus 4.1786 times 3. So Y cap is equal to 83, around 83. What we don't know yet is how reliable our prediction is because we have information only on a sample of students, not the entire population. So, just how accurate is our estimate based on the information we have? To answer this, we need to construct a confidence interval around our predicted exam grade to get a feel for the accuracy of the regression line. Recall from Chapter 8 that confidence intervals provide an estimate of a population parameter based on a sample statistic. In this application, our confidence interval will provide a range of grades students can be confident of achieving if they study for a particular number of hours. To construct such an interval, we first need to determine the standard error of the estimate using equation 14.16. The standard error of the estimate measures the amount of dispersion of observed data around a regression line. If the data points are very close to the line, such as in the graph on the left in figure 14.14, the standard error of the estimate is relatively low. The graph on the right in figure 14.14 shows a larger standard error because the actual data points are farther from our regression line. We may claim that a smaller standard error of the estimate is more desirable than a larger one. In our regression line is used to estimate the dependent variable or exam grades given a value for the independent variable or hours of study. It will be more accurate if the data points are close to the line. That is why we call it the standard error of the estimate. Using our grade data from the previous section and equation 14.16, the standard error of the estimate is calculated as follows. SSE is equal to 74.62, so SE is equal to 4.32. Make a note of this value because we will be using it in the future calculation in the chapter. Our next step is to calculate the confidence interval for Y or the grade around an average value of X or the hours of study. The confidence interval for an average value of Y based on a value of X. Notice that the first student in our sample studied 3 hours and earned a grade of 86. Our regression line predicted the student grade would be an 83. Now, I hear your curious mind asking, I wonder what the 95% confidence interval would be for the average exam score for students who studied 3 hours. Well, you've come to the right place. The answer to this excellent question lies in equation 14.17, where CL equal the confidence interval for an average value of Y. Y cap is the predicted exam grade for a student who studies 3 hours. T alpha divided by 2 is the critical t-score from the student's t distribution. SE is the standard error of the estimate. N is the number of the ordered pair. X bar is the average value of X from the samples. Now, before you start regretting your question, let's put this equation to work one step at a time. From previous section, we have determined the following values. Y cap is 82.7, S is 4.32 and 6, and sigma x is 22, and sigma x squared is 90. We need to calculate the average value of X, or hours of study, as follows. X bar equal to summation of X divided by N is equal to 3.667. To find our critical t-score, T alpha divided by 2, we look at table 5 in Appendix A. This procedure has an n minus 2 equal to sig minus 2 4 degrees of freedom. For alpha equal to 0.05 and a two-tailed test, we find that 2 alpha by 2 or divided by 2 is equal to 2.776. We can also identify this critical score using Excel. T.inf.2t inside the parentheses 0.05, 0.4 equal to 2.776. Using equation 14.17, our confidence interval is calculated as follows. We can describe this confidence interval with the upper confidence limit or UCL and lower confidence limit or LCL as follows. UCL is equal to 82.7 plus 5.55 equal to 88.3, and LCL is 82.5 minus 5.55 equal to 77.2. What does this interval mean? Let's define our population as all of the students who took the statistic exam. Our sample consists of only 6 of these students. Based on this grade, we predicted that studying 3 hours would result in an exam grade of 82.7. However, because we don't have data on the entire class population, we cannot guarantee that everyone who studies for 3 hours will earn this grade. However, we can say that we are 95% confident that the average exam grade earned by all of the students who study 3 hours will be between a 77.2 and an 88.3. This interval is shown graphically in figure 14.15. The weight of the confidence interval, which is shown in red, changes depending on the value of X or hours of study that we choose. The weight on X equal 3 is as follows. 88.3 minus 73.2 is 11.1. The interval is narrowest at the average value of X in our sample, which is as follows. As we construct intervals for larger and smaller values of X away from this mean, the interval widens, as the table 14.5 shows. As a result of this effect, our estimate for the average grade is more precise the closer we are to X. The prediction interval for a specific value of Y based on a value of X. In the previous section, we constructed a confidence interval for the average grade of all students in the population who studied 3 hours. What if you would like to know what the interval of grade are if you study 3 hours? This is a different question than the one we answered in the previous section. Here we are looking for a prediction interval for an individual grade rather than a confident interval for an average of grade. The prediction interval is shown in equation 14.18. Notice that this equation is identical to equation 14.17, except that we add 1 in the square root. Let's use equation 14.18 to determine our 95 prediction interval if you study for 3 hours. We can also describe this prediction interval with the upper prediction limit, or UPL, and lower prediction limit, or LPL, as follows. UPL equal to 82.7 plus 13.21 equal to 95.9. LPL equal to 82.7 minus 13.21 equal to 69.9. As you can see, our prediction interval is much wider or less precise than our confidence interval from before. Recall from chapter 7 that samples mean have less variation than individual values from which the sample is drawn. Because our prediction interval is estimating a single value, the variation will be much greater than we are estimating an average grade. If we want a more precise or narrower estimate for our grade, a larger sample size would help achieve this objective. Thank you.